Great. Yeah. So a very warm welcome to IOA. And my name is Jiachen Jiang, and I'm a research fellow here at IOA. And I will be talking about black holes today. So after reading the title of my talk, you may be wondering, wait, can we actually run away from a black hole? I thought a black hole is an object, nothing can escape from it, not even light, and that's the reason why it's called a black hole. And you're definitely right. That's the reason I'm going to put a small footnote after the title of my talk, saying that we're going to discuss materials that can run away from a black hole before they get too close, okay? So recently, we astronomers have found that materials can not only orbiting around the black holes or moving in the direction of a black hole, instead they're actually outflowing, which means, if you may call it, they're running away from a black hole. And their velocities can be very high. They can reach a significant fraction of speed of light near a black hole. And this is what we call a black hole wind. So this is shown by the blue streams of materials in this picture here. This is not a real picture of a black hole. This is an artist's impression, by the way. The mechanism behind these black hole winds is still under discussion, but tonight I'm going to introduce to you one of the theories, at least the one explained quite a lot of astronomical observations of these black hole winds. Since I'm going to talk about black hole, I have to start with this very famous image of a black hole. This is a real astronomical image of the supermassive black hole in M87. The dark region in the middle, that's where the black hole is. And then you see this very bright ring. That is the disk of a glowing gas swirling around the black holes. Okay. And here is an artist's impression of what a black hole accretion disk looks like. So you have a black hole in the center, and then you have gas, dust, plasma orbiting around the black hole that forms the disk here. Okay. And if you look at this picture very carefully, you would notice there is a red side of the disk and a blue side of the disk. Okay, so imagine if there is a black hole over there and the materials are orbiting around it, these two sides corresponding to approaching side of the disk and a receding side of the disk. So on the receding side of the disk, the materials are moving away from us, moving away from the observer, and the approaching side of the disk, the materials are moving towards us, and they have different colors. The reason behind their different colors is the Doppler effect. Okay, we have actually a lot of Doppler effects in our daily life. For example, imagine if you're standing in a road and a car is approaching you very quickly. I would not suggest doing that because it's very dangerous. And then the driver sounded the horn to warn you the car is coming, and you can hear the horn very loudly, okay, at a very high pitch. And then you step out of the car's way because you don't want to get hit. And then the car just moves away and run away from you. And then you hear the horn again. Now it sounds different at a lower pitch. Okay, and this is the Doppler effect. To better demonstrate what I just said, I'm going to play a small clip, a short clip of this. Did you notice the difference in the pitch of the car horn?
The Doppler effect.
So this is the Doppler effect, okay? Oops. Yes. So the Doppler effect applies to all kinds of waves, not only sound wave, but also light waves, okay? So the materials are orbiting very fast around the black holes. So on the approaching side of the disk, the light from the materials on the approaching side of the disk moves to a higher frequency, which means they tend to look bluer. And on the opposite side, materials are moving away from us, and their color tends to be redder. So this is the Doppler effect. So based on the Doppler effects, we can actually study the movement of materials around the black hole. And we astronomers have found that materials can orbit around the black hole or flow into the black hole. And also, we find some materials can actually run away from black holes, so they are outflowing. That's how we find it, based on the Doppler effect. So the emission of these outflowing materials, their light, are not at the frequency or wavelength they're supposed to be. Instead, they're shifted to higher frequency or longer wavelengths, if you may like to call it, due to Doppler effect. That means they are moving away from the black hole, and this is when we find black hole winds. Black hole winds are a relatively new topic in our field. It's very interesting because it means a lot of mass tries to get into the black hole, and meanwhile, a lot of mass gets ejected back out through these winds. This forces scientists to think really hard how we can actually build up like these supermassive black holes to be so massive. I really like this analogy. It's just like feeding a baby. You try to feed a baby some food, but a lot of food gets spit back out. Eventually, you get some food into the baby. The baby gets its nutrition, the baby grows, but an awful lot of food gets spit out. That's what is happening here. A lot of mass try to get into the black hole, but meanwhile, a big fraction of these mass get ejected back out through the wind. To understand the mechanism behind the wind, we first need to understand how gravity works. So we're going to start with something closer to us. So here is a GIF of our solar system. So there is a sun at the center, and then we have a few planets, like the Mercury, the Earth, the Mars, because the gravity is stronger when the orbit is closer to the sun. So the Mercury actually has the highest orbiting velocity among all the planets, and the planets that are further away, they have lower velocity. For example, the Mars and Earth, we orbit around the sun with a lower velocity. So this is the similar case for materials around the black holes. Okay, so the materials that are closer to the black hole, they move with a higher velocity, so they move faster. And the materials that are further away from the black hole, they move with a lower velocity or they move more slowly. And bear in mind, the black hole here doesn't have like individual planets like our solar system, but instead it has a disk, which means the mass is continuously distributed on this disk. So different parts of the disk, they have different velocities, okay? And that also means there's a lot of friction going on in the disk. This is just like on a very cold winter day, you try to rub your hands to heat up, okay? The friction between your two palms that have different velocities can heat up your hands, okay? So it's the same what is happening in the disk. There's a lot of friction going on due to different velocities and turbulence and all of this stuff, and that heats up and it warms up the disk quite a lot, okay? When I say the disk is very warm, I'm not talking about a 40-degree, 30-degree heat wave we experienced last summer. I'm talking about 1,000,000 degrees, okay? So it's really, really hot. It radiates away a lot of heat, the black hole disk, okay? And when I say it radiates away a lot of heat, it also means it gives away a lot of light. That's what the nature of the heat is. It's basically radiation of light. So here is a thermal image in the infrared band of a human body. Okay, as you probably know, the temperature of a human body is 37 degrees, unless you have a fever due to COVID. Anyway, that also means our human bodies are glowing in the infrared band. Okay, so this is what it looks like. We actually try to set up a thermal detector for you guys to see yourself in the infrared band. Unfortunately, we didn't make them work. But however, I found this amazing clip of documentary. It shows us in nature, we actually have some animals. They have vision, a thermal vision, or you can call it infrared vision of the world. That's how they see their enemies in a dark night. So this is an example of a snake.
Constantly emit heat in the form of infrared radiation. The camera senses this infrared in amazing detail. It means Michael can record the snake's movement in total darkness.
This camera is really useful for us here tonight because it allows us to see basically what the snake is seeing. We are looking through a snake's eyes when we use this infrared sensitive camera.
The goal of this experiment is to see whether the snake can sense a warm object in the pitch black. The target is a black balloon filled with warm water. To the snake, it should look like a warm-blooded mouse or a small rat.
We'll have that balloon swinging back and forth like a pendulum. The balloon is black, the background is black. We'll actually turn the lights out for you here. So there's no visual contrast. The idea is that there should be no way to see that balloon. The only difference between the balloon and the background should be thermal contrast. The balloon is warm, the background is relatively cool.
Handling a large python in the day requires great care. It's even more difficult in the dark. Michael covers the snake with a box until he's ready to start the experiment.
These snakes have lots of teeth, so if they bite you, you know it.
But for Michael, it's worth the risk. If the experiment works, the footage will be a world first.
So after the lights are off, we'll remove the box from the snake. The snake will be free, and hopefully we'll see some very interesting behavior. We'll learn something new about this amazing, unusual sensory system.
In the pitch black of the swamp at night, conventional vision is useless.
It's really dark. I can barely see to get this box off the snake. I'm afraid I might look like a warm balloon to this snake. We'll uncover the snake. It's a good thing we have this infrared camera. Otherwise, I'd have no idea where the snake is.
The sensitive infrared camera picks up the faint heat of the snake as a vivid orange and the warm balloon as a bright white.
Here he comes. Tongue flicking at it, moving his head with it. He definitely sees it. He definitely sees it. He's got eyes, but it is pitch black dark out here. So something else is telling him that that balloon is there. It is absolutely dark. It cannot be using its eyes, but it's following the motion of that balloon. It knows that balloon is there.
Great. So that is telling us that our body is warm and we're glowing in the infrared band. Okay. And remember that the black hole disk is similar. The difference is that it's much, much hotter. We're talking about 1,000,000 degrees. So instead of glowing in the infrared band, it is glowing a much, much higher energy bands, much, much lower wavelengths, and that is ultraviolet. And the environment around the black hole, they have X-ray emission as well. So it's a really high energy light going on around the environment of a black hole. So the environment around the black hole is so hot, it's radiating so much light, and the radiation is so powerful that it can actually interact with the particles, okay, and applies a certain pressures on object. So the light actually pushes things away, and this is what we scientists call radiation pressure, okay. Funny that my talk is made of a lot of YouTube videos. Here's another YouTube video showing you what radiation pressure is. It is from a physics lecture this time.
The average pressure, real. Can we really have a way to show you radiation pressure? So I've got a couple things here. First, I have extremely light paper. So this is lens cleaning paper from my lab. We use it to delicately clean little microscope objectives, and it's very light. It's like mostly air. There's a little bit of mass to it. So this is very light, and this is my green laser pointer, which I have sort of juiced up a little bit. So, I mean, it's still legal, but it's a fairly powerful green laser pointer. So I'm gonna shine it on the back of this, and a lot of the light will scatter back because it's white. So we'll get sort of a 2p, or a double minimum kick, and we'll see if anything happens, see if we can make it move a little bit, okay? So it doesn't make a big motion, so you gotta look really close. That's why we have the close camera. And now this thing bounces around with the air conditioning, and I think the air conditioning's calm enough. Here we go. See that? Fell over. Let me try again. If I can get it down on it quick enough, it might actually slide. Amazing. Radiation pressure. How many believe me? Of course it's not.
So this is radiation pressure. So basically light can push things away. Unfortunately, I cannot do this experiment here because, as you probably ever heard, he modified the laser pen a little bit to make it more powerful, although it is still legal, but anyway. And later we're going to do stargazing later. We're going to use a laser pen there too. Don't worry, that one is not. It's definitely legal and definitely safe, okay? Don't worry about that one. So that is radiation pressure. So everything is put together now for the black hole wind. So basically, we have a lot of radiation going on near the black hole, and the radiation just pushes the materials away and forms wind, or you may call it, these materials can run away from the black holes due to the radiation pressure. Okay, and I just mentioned that we actually find all of these black hole winds in spectrum. That's when we see the light of these outflowing materials shift to higher frequency due to Doppler effects. That's how we find them. But you may ask, can we actually see these winds in images? Unfortunately, it's very difficult because all of these winds, they happen in a very compact object near a black hole. So they're really teeny tiny little dot in our night sky. With our current technology, there's no point for us to resolve the shape of the wind and all of these things. Okay, but we do have a lot of other examples of radiation pressure in our universe, in other objects of our universe. So get ready to be blown away by radiation pressure because I'm going to show you some real astronomical images of radiation pressure in our universe. This time, promise you, not artist's impression anymore. So this is the Hubble Space Telescope of the Helix Nebula, which is only 700 light years away from us. What we are looking at is, at the center, there is a remnant of a dying star. Okay, this will happen to our sun a billion years later, but now you're safe. Anyway, the light of this dying star is just pushes dust and gas away and forms this amazing, like eyeball-shaped image in the sky. And here, if you look at this nebula in the infrared band, you can really look at very detailed structure of the dust being driven by the radiation pressure, which is really cool here. And here is another example of a radiation pressure, not only dying stars, but also newborn stars. So all of these bright dots in these images, they are newborn stars, they're only a million years old. And all of these shades, dark shades you see, these are all dust, and they are being shaped by the radiation from all of these newborn stars, and it forms this amazing oil painting-like image in our night sky. You may have heard JWST as well. It's one of the, the latest, biggest telescope we have, space telescope we have. What you're looking at, the bright spot in the middle, that is a binary star, which means there are two stars orbiting around each other, and they create these periodic ripples of dust, and the radiation from this binary system just pushes the shells of dust, after one shell after another shell, and it expands in the space. Okay. Another example of radiation pressure is the comet. For example, when a comet is very close to the sun, the radiation pressure of the sunlight will blow the dust on the comet away, and it forms this very long tail there. So the sunlight basically comes in from the direction, from the bottom there, okay? That's where the sunlight comes in, and it blows the dust away and forms this dust tail. So I think that's almost it. So at the end, I hope I have convinced you that the radiation mechanism is a very fascinating topic in astronomy, and it is responsible for a lot of amazing figures you just saw, and also it provides a way for materials to run away from a black hole. That's it. Thank you.
Okay, warning that the lights are about to get bright. It can be shocking. Okay, so our observers are just sort of finishing setting up. I'm sorry. Before we do that, do we have any questions for JJ? Do you mind if I get onto the computer while you do questions?
Yeah.
I don't believe there are no questions at all. There you go, yes.
Hello.
So I don't know how to say this, so I'm going to, because I don't have the right terms, and it's really embarrassed, but how does the energy of gravity go against radiation pressure? I mean, if we have radiation pressure, shouldn't everything go out? Or how do they contrast?
That's exactly what we are studying right now. So if the radiation pressure is very strong, that's a lot of cases we see in very bright sources, because there's a lot of radiation, we actually see all of these wings. But in fainter sources, you sometimes see wings too, but they're caused by different mechanisms, not necessarily radiation pressure, but other stuff. But in most cases, no, it's just a gravity sucking things into the black holes.
So gravity is stronger than radiation?
Yeah, exactly. That's what there's a competition. Is that force the materials to go in or force the materials to go out? Yeah.
And you can measure that, so if astronomers know that gravity will be stronger than radiation pressure, or
You measure the amplitude of the forces. I would say yes, roughly. Roughly, because there's a lot of uncertainty. Yes, roughly, yes. Yeah.
Right. Is it possible for radiation pressure to be stronger than the force that holds up a neutron star?
Holds up a neutron star? Like?
Yeah, a very compact star. It's a very small star.
Yeah.
And gravity is holding it together, but it's not turning into a black hole.
Mm-hmm.
But is it possible to get more radiation pressure to stop a more compact object from
falling on itself? That's the question. Yeah.
Yeah. So is it possible to have so much radiation down there that it will be stronger than what's holding up a neutron star, so therefore preventing an object that's too compact to be a neutron star from collapsing into a black hole?
That's actually a good question, though. But so far, the most radiative ones, they're already compact objects. So they're already neutron stars or black holes. They're already very radiative. And they're the result of stellar collapse. So it's after these things happen, and then it starts having radiation pressure, having a lot of radiation. And it's the total radiation that has a lot of pressures. So you're discussing that in maybe different shells of these stars. Maybe only the inner bit has a lot of radiation that blows things the outer bit away. But it's actually the total radiation is more important. And in our case, it's actually not the radiation from the black hole itself, but instead it's the disk around the black hole that is radiating a lot of light and pushes things away.
So if something is about to be compact enough to be a black hole,
Yeah.
it could give off so much radiation that it would hold up.
Oh, I don't have the, may I just show you that is what is happening here. So that is a dying star. Now it's a white dwarf. So it forms a compact object, and its light just blows things away.
Yes, the light comes off this, those things away.
Okay, should we press the friend? Maybe you can talk afterwards if you've got
Yeah,
some
sure.
more questions, and maybe give someone else a chance if anyone has any sort of final question before. Okay, sorry, I missed your arm. There you go.
How exactly is a black hole formed?
That's a good question. That's one of the biggest mysteries in astronomy. It depends on what kind of black holes we're talking about. Today, I'm going to talk about supermassive black holes. And if you remember what I said, the wings are one of the mysteries, because the wings actually carry out a lot of mass out of the black holes. It kind of like stops us from feeding the black holes from the galaxy and all of the things. So that's one of the biggest mysteries. How could we build up such massive supermassive black holes in our galaxies, where we still have these strong wings carry out so much mass out of it? That's one of the biggest mysteries. And yeah.
It's a really nice way of saying we don't know.
We don't know. Yeah, exactly. Short answer is we don't know.
Okay, wonderful. Okay, so my colleague outside, Natasha, will lead you to the stargazing. Just a bit of housekeeping to kind of show you where you're going. So we can go back to, where are we? Where did the thing go? There we go. Okay, so you are currently here. You're going to be led sort of out here onto the lawn here. And so out here there'll be a floor show where you can sort of like see all kinds of nice things projected on some screens. There'll be some narration to take you around the night sky. There'll be a telescope here as well. This is one of our historical telescopes, nearly 200 years old. That's going to be looking at some exciting things. This one you won't be able to miss. This one you will be able to miss. So go and visit it because they get very lonely in here. You have to kind of like, this is the kind of lawn area, then you have to kind of go through the trees here, and there'll be this telescope here. I'll be around to kind of point you in the right direction. But just bear in mind, sort of off down here, there is another telescope, which I think is currently looking at Uranus. So some very exciting stuff there. So, before we stargaze, can we thank JJ again?
Thank you.
Wonderful. Okay, so if you all follow my colleague Natasha, they will lead you to the stargazing.
Do you want me to turn off the computer? Or
No,
have it-
I'm going to stay around to shut the lecture.
Okay, cool. Good, thank you very much.
Cool.